Okay, good morning. So today what we're going to do is we're going to focus on the third type of reaction. We first looked at precipitation reactions, which were an example of a double replacement. We then looked at acid-base reactions, also an example of double replacement. And now we're going to look at oxidation reduction, okay, or sometimes referred to as redox reactions. Redox reactions are interesting because they involve the movement of electrons from one reactant to another. So for example, a chemical battery uses an electromotive force to drive electrons from the anode through a circuit into the cathode. So electrons are moving from atoms, from one atom to another, from one element to another. So we're going to look at the sort of the introductory details of redox reactions. And we'll start by looking at a set of guidelines we can use to determine whether a reaction is a redox reaction or not. Because sometimes when you look at these chemical equations, they all kind of look the same. So how do you tell if something is a redox reaction? What we did for precipitation reactions was we looked and we saw, oh, wait a minute, we have two ionic compounds dissolved in water, and we had one product that was a solid and the other one was aqueous, so it dissolves in water. So those, the existence of those ionic compounds and the formation of a solid, that kind of tipped us off that that was a precipitation reaction. For the acid-base reaction, we had a couple of different ways of analyzing it. One was through the idea that we're transferring a hydrogen ion. If we saw a hydrogen on one of the reactants, that was a clue that it could be a acid-base reaction. We then looked and saw, oh, well, we have a hydroxide in one of them and a hydrogen ion on the other. That's probably an acid-base reaction, okay? What we're gonna do with redox reactions, there's a couple of different ways to analyze them. The first way is through what are called oxidation numbers. I guess the older term for this would be to call them oxidation states. So you'll see that terminology out there as well. Okay, come over here. There we go. Typically oxidation numbers are what we use right now. Now here's the idea. Essentially what we're doing is we're saying, look, you've got an atom, let's say it's a sodium atom, and you've got a chlorine atom. And what we're claiming is that electrons are being transferred from one substance to the other. Now, the electrons are coming from what's called the reducing agent. So the reducing agent is the substance that kind of gives up these electrons. And the electrons will flow into what are called the oxidizing agent. Agent meaning the same thing as reactant. Okay, so the oxidizing agent is the acceptor of the electrons and the reducing agent is the donor of the electrons. Okay, now notice what happens. Each of these have a charge of 0. A sodium atom, even though we never really write this, it actually has a charge of 0, right? It doesn't have any charge. And the chlorine atom, same thing. It doesn't have any charge. So we could, in theory, write a 0 there. We don't generally do that, but they are neutral. And what's happening is now the sodium has lost an electron, right? It doesn't have that electron anymore. It still has 10. But because it lost an electron, it now has a charge. It's now positively charged, right? If you lose a negative charge, you become positively charged. Likewise, the chlorine is no longer an atom. It's now an ion. It now has a negative charge. So that electron is transferring a little bit of mass. There's a tiny change in mass. The electron's not a very heavy particle, but it is charged. It's transferring over quite a bit of electrical charge. A one entire unit charge is a big change for an atom. Okay, so what you end up with then is a sodium ion, right? So we write that as Na plus, and we write the chlorine as an anion. So that would be Cl minus. So here's the chemical equation. Here's a little sort of diagram of what's happening. So what that tells us is that if atoms if their charges change, right? So we saw a change in charge, right? It went from 0 to +1. That's a change. That's an indicator that it's a redox reaction. We generally don't see that with acid-base reactions or with precipitation reactions. A sodium ion in a precipitation reaction is still going to be a sodium ion at the end. And likewise, a hydrogen ion is still going to be a hydrogen ion at the end in an acid-base reaction. However, in redox reactions, the charges of these atoms change. Likewise, the chlorine had a charge of 0, and now it has a charge of -1. Okay, so for that reason, we want to develop a system that can kind of tell us how the charges are changing in a reaction, and then that will allow us to analyze redox reactions. So those are called oxidation numbers or oxidation states. And there's a general set of guidelines for them. And I'm going to write them down here. The first guideline is that elements have a charge of 0, right, 0, and an oxidation number of 0. Okay, so in this case, for elements, the charge is equal to the oxidation number, okay, 0. So we would, in this equation, we would say, look, the charge here is 0. It's an element, right? Sodium is an element. The charge is equal to 0, so the oxidation number would be equal to 0. The chlorine atom here has a charge of 0, so it has an oxidation number of 0. So that's our first guideline. The second one is that monatomic ions have oxidation numbers equal to the charge of the ion. Okay, so you can see here, we are really trying to relate oxidation numbers to charge. Anytime we can get away with it, we're going to make the charge equal to the oxidation number. We'll see in a little bit that you can't always do that, and we have to play some tricks, but we're going to try to make the charge equal to the oxidation number. So an example of that would be these two over here. Those are monatomic ions. A monatomic ion is an ion that has only one atom. So that would be sodium. So we would say that the sodium ion right there, or the sodium cation, if you want to be more specific, it has an oxidation number of +1. Now, unlike charges in chemical formulas, when we write down the oxidation number, we put the sign first and then the number. So we write +1 as the oxidation number. In the chemical formula, we often put the number as a superscript and then the symbol for plus minus. But for oxidation numbers, we put the sign first and then the number. Likewise, the chloride ion has a charge of -1, so its oxidation number would be -1. So far, so good. Now, for this particular equation here, which is very, very simple, what it shows us is that the sodium changed its oxidation state or its oxidation number. It went from 0 to +1. That tells you it's a redox reaction. If any substance in the reaction changes its oxidation number, that means it's a redox reaction. And that wouldn't be the case for a general acid-base reaction or precipitation. They will not change oxidation states unless they are also redox reactions. So you can have some reactions that are acid-base and redox, but in general, acid-base reactions, their oxidation states don't change. Okay, so there we go there. Now, what we're going to say is that for polyatomic ions, the sum of all oxidation numbers is equal to the charge of the ion. Okay, so this is a different thing situation here. Now we're talking about polyatomic ions. So that's an ion that has more than one atom. Now what we're saying is that if you add up all the oxidation numbers in the ion, so every atom has an oxidation number, could be 1, could be -1, could be -2, could be +1, +2. In general, we're going to have them be whole numbers. There are some substances where they're not whole numbers, but usually they're whole numbers. They have to add up to the charge of the ion. Okay, so an example of that would be the phosphate ion, PO4 -3. Each atom in that polyatomic ion, there's 5 atoms, right? 1 phosphorus, 4 oxygens. All 5 atoms have an oxidation number. You add them all up, it's got to equal -3. And we'll make an assumption, which is that within one polyatomic ion, if there's more atoms, if there's more than one atom of the same element, so for example, there's 4 oxygens there, we'll assume they all have the same oxidation number. We're not going to assume that one oxygen is -2 and the other one is -1. We'll assume they all have the same oxidation number. Okay, we'll go through the elements with what their oxidation numbers are in a little bit. Okay, the next rule is that for compounds, okay, so what's an example of a compound? H2O, right? Sorry, H2O. H2O is a compound. It has 2 different elements. It's neutral, right? For compounds, the sum of the oxidation numbers equals 0. Zero, right? And there's a logic to that, right? If the sum of the oxidation numbers in a polyatomic ion are equal to the charge of the ion, then the sum of the oxidation numbers in a compound should equal 0 because a compound is neutral. You could think of a compound as a neutral polyatomic ion, right? A polyatomic ion is really a charged compound, and in most cases anyways. So there we go. So this got to add up to 0, okay? Now, the next step, I don't want to erase this here because it's, I want to have it next to us here, so I'll get rid of this. The next issue is, well, that's fine. So we can figure out the oxidation numbers of monatomic ions pretty easy. But if we don't know any of the oxidation numbers of any of the elements, then knowing that they add up to the charge in a polyatomic ion or knowing that they add up to 0 in a compound, that doesn't help us because we don't know, for example, in water, that's fine, they add up to 0, but what's hydrogen and what's oxygen? So for that reason, we have another set of guidelines. And these are for the different elements in polyatomic ions and compounds. Right? We don't have to worry about them if they're pure elements. So for example, sodium is 0. We don't have to worry about that. So elements themselves aren't important. I mean, they're important, but they're not necessary. We have to worry about them. And the same for monatomic ions because the charge of the monatomic ion is the oxidation number. But when we get to these compounds and polyatomic ions, we have to know what each atom is. So here's how we go about it. We have a set of guidelines. And the first guideline is that fluorine is equal to 0. I'm sorry, is equal to -1. I don't know why I said 0. Fluorine. So that's F for fluorine, right? So let me write the element name over here. It's going to be -1. So if you have any polyatomic ion or any compound, your first thing to do is you set the F to -1. Okay, that doesn't really change. The second one is that hydrogen is going to be +1. Okay, so this is hydrogen. Okay, now there is an exception to that. And the exception are what are called hydrides. So I'm going to write here an exception, hydrides. So if I have a metal, so you look at the chemical formula, see how you have a metal here, sodium's a metal, and then you have a hydrogen. in that case, the hydrogen is -1. So I'll write it in parentheses. So in this case, the hydrogen is -1. That's called a hydride. It's very reactive. It does exist, but it's very reactive. It's sometimes used to kill bacteria, to keep things from growing in a solution, because it's so reactive. That hydride wants the hydrogen wants to get rid of electrons. So it will react with all sorts of things, okay? But generally, 99% of the compounds you'll ever see, we're going to say that hydrogen is +1, compounds or polyatomic ions, okay? Third one, oxygen is -2. Isn't that cool? Okay, so this is oxygen. Again, there is an exception to that. And the exception is called a peroxide. And you're familiar with one very famous peroxide, which is H2O2. So in this case, oxygen is -1. Okay, so it's generally -2, but in the case of a peroxide, you can often see, well, there aren't very many peroxides out there. The hydrogen peroxide right here is by far the most common of the peroxides. You really have to go into doing organic chemistry to see other types of peroxides out there. They do exist, but they're relatively rare. The main focus for us will be dealing with oxygen being -2. If you have a contradiction, so if it doesn't work out that you can have F be -1 and O be -2, the first rule, the F, the one that's higher up, supersedes anything that comes after it. So fluorine is the dominant guideline, and then hydrogen, and then oxygen. Okay, so those are the three important elements. The next thing I would say is that if you have a compound, an ionic compound, so let me write this down here. So this is for ionic compounds. To find the oxidation numbers, break the compound into its ions. Okay, so break it up into its ions. So for example, if I had a compound like MgCO3, that's an ionic compound. You got magnesium, which is a metal, and you got carbonate, which is a non-metal. Break it up into the ions first and then analyze it. So you break this up into magnesium 2. Remember, magnesium is in the second group, group 2A, so it's +2. And then you got your carbonate ion over here, right? That's a polyatomic ion. So the first thing you do with an ionic compound to do the analysis is you break them up into separate ions. So now that magnesium becomes a monatomic ion, right? As a monatomic ion, we have a little rule here. The charge of the ion is equal to the oxidation number. Okay, so it'd be +2. And what that does is it simplifies things, because now instead of having 3 different elements that you have to analyze, and we don't have a rule here for magnesium or carbon, you now have magnesium by itself. Now we've got that one. The carbon we don't have a rule for, but we do have a rule for oxygen. So but if you can get things down to 2 elements, and there's a rule for one of the element, you can find the other element from that first rule. And if there's 3 elements and you have a rule for 2 of them, then you can get the third, but you can't get 2 elements. If you have 3 elements and 2 of them you don't know, you can't figure them out unless you break them up into ions like I just did. Okay, so let's go through an example. So those are our rules there. Let me, I guess I'll just save this to photos so that we have it. Let's go through an example of assigning oxidation numbers. Essentially, this should be enough for us to be able to go through them. And every textbook kind of words the oxidation numbers slightly differently. They order them differently and all that kind of stuff. But these are essentially what we have. So let me stop that one. And come over here. Let's see. Okay. Here we go. So here's a typical problem. Assigning oxidation numbers. That's our first step. Some chemical reactants are listed in the table below. Okay, so these are reactants. Complete the table by filling in the oxidation state. So they use the word state instead of number, that's fine, of the highlighted atom. So in the highlighted, they mean in red, okay? So the first one is copper oxide. So that's actually the compound that we used in the laboratory, right? Recently this week. So copper oxide, and we just want to know what the oxidation number or the oxidation state of the copper is, okay? So here's what you do. You look at your guidelines, you look at your rules. You can see right there that that's an ionic compound. It's got a metal with a non-metal. So there's a couple ways to analyze it. One way would be just to break it up into ions, right? Take your ionic compound and break it up into ions. So let me actually, I'm going to do this. There we go. Okay, so we break it up into ions. Well, how do you figure out the charges? Well, we know that oxygen is in group 6A, so that means it's -2. There's one copper, one oxygen, so that tells you that the copper's got to be +2. And now what do we have here? We have monatomic ions. Those are both monatomic ions. One atom, right? And so our guideline says that monatomic ions, the charge of the ion is equal to the oxidation number. So the oxidation number of copper would just be +2. Okay, so there's your copper, +2. Now let's write it down here. Now there is a slightly different way you could do this, and that is to not consider it being an ionic compound, but just consider it being a compound. What we said was that for a compound, the oxidation states have to add up to 0, and that's a compound, right? So they have to add up to 0. And then we had a rule for oxygen. The rule for oxygen is that it's -2. Well, if the oxygen is -2, the copper would have to be +2 for them to add up to 0, right? So mathematically, what you're doing, I'm going to use the symbols of the elements. You're saying that the oxidation state of copper plus the oxidation state of oxygen has got to equal 0 because it's a compound. And then you're going in and you're saying, okay, well, there's no fluorine in there, there's no hydrogen in there, but there is an oxygen, and oxygen is -2. So then you would say, okay, copper plus, I'll put this in parentheses, -2 is equal to 0. Add 2 to both sides so that you can isolate the copper, and you get +2, right? If you add 2 to this side, you get 0. If you add 2 to this side, you get +2. And that's a different way of telling you that you've got a +2. So slightly varied ways of doing those two, of doing that particular problem, but you get the same answer. Okay, let's take a look at the second one. The second one is very simple. It's just H2. That one's easy. Why is that easy? It's an element, right? This is just an element. Element, we have a rule for that. It's got to be 0. So each hydrogen has got to be equal to 0. Okay, so the oxidation state or the oxidation number of each atom is 0. 0 plus 0 is 0, right? Okay, elements are easy. The next one is CF4. And they want us to do the carbon, which is good. That's what I would recommend. If I were making this problem, you want to do the carbon, and then it's CF4. This is called carbon tetrafluoride, right? 4 fluorines, 1 carbon. Okay. All right, well, we don't have a rule for carbon. This is not an ionic compound, right? Carbon is a nonmetal, fluorine is a nonmetal. They're on the right side of the periodic table. So this is a molecular compound. So it's not an ionic compound. So we're not going to break it up into ions. Very common, people will do that when they're first learning to do these problems. They'll take every compound and break them up into ions. We only break them up into ions if they are ionic compounds. And if they're ionic compounds, you're going to find a metal in there. This is a molecular compound, so we don't break it up into ions. So we do have a rule for fluorine. Fluorine is -1. In fact, that was the first rule. So here's how we go about it. I'm going to show you in terms of a picture, just so you can kind of see it as a picture. So imagine you've got a carbon and 4 fluorines attached to it. That's really what carbon tetrafluoride is. Okay, this is a compound, right? It has 2 different elements, 2 or more elements, and the charge is 0. So it's not a polyatomic ion, it's a compound. So what is the rule about compounds in terms of oxidation states? They have to add up to 0, right? So they have to add to 0. When you add them all up, they got to be 0. So let's do this. We don't have a rule for carbon, so I don't know what that is, but I do know that each fluorine is -1. So really, then you just ask yourself, what does that carbon have to be so that when you add it to all those negatives, you get 0? And the answer is +4. Think about it, right? If you make this a +4, and these are all -1s, you're going to get 0. They're going to add up to 0, right? So that tells us the carbon has got to be +4. And again, for oxidation states, you put the sign ± and then the number. Now here's an algebraic way to do it. Let's do it algebraically. What we're going to do, we know they have to add up to 0. So I'm going to write it using symbols. Carbon is 1 element. And how many fluorines do we have? We have 4. So I'm just doing this for mathematical reasons. They have to add up to 0. And as I said earlier, if you have more than 1 atom of the same element, you assume they're all the same. There are some weird compounds where you might have a nitrogen is +1 in part of the molecule and -1 in a different part of the molecule. That kind of stuff can happen, but we're not going to worry about that in this course. Okay, so we'll assume that each fluorine is the same and each fluorine is -1. So what do we have? We just substitute in -1 for each fluorine. And that's going to be equal to 0 because it's a compound. So that would algebraically be C -4 equals 0, right? Why -4? Because 4 times -1 is -4. So adding -4 is the same thing as subtracting 4. So algebraically, you add 4 to both sides. So C -4 plus 4 equals 0 plus 4. You add 4 to both sides. So now, as a result of that, you get that carbon is equal to +4. And you get the same answer that we got out here as a diagram. I would prefer that we do it this way, algebraically, because this will allow us to do more complicated substances. But we don't do super complicated substances, so you could actually do it drawing little pictures like this. Either way, it would work. Okay. We got one more in this problem set, and it's the Cu plus 1, sorry. So let me save this one. So in this one, they say do copper plus. Okay. Copper plus. All right, Cu plus. Okay, well, there's only 1 atom and it's an ion, so that's a monatomic ion. Cool. Well, what's a monatomic ion? The charge of the ion is equal to the oxidation state. So that means for copper 1, it would be +1. Okay. And that's assigning oxidation numbers. Now for that one, the 4 that we did, there weren't any polyatomic ions. So I'm just going to scroll ahead here and see if I can find a polyatomic ion. Well, there's one there. So I'm going to do 2. I'm going to do 2 more problems. We'll do these 2. That one. And oh, let's do this one here. HCO3 minus aqueous. And then for this one, they want you to do the carbon. There we go. And then for this one, they want you to do the vanadium. Oops. V2O5. That's vanadium oxide. Vanadium's a transition metal. So let's try these two. Let's do the vanadium oxide.
GCNE. And last name is ATAYA.
All right, so V2O5. First of all, let's identify that as a compound, right? So that means they have to add up to 0. Okay. We do have a rule for oxygen. We do not have a rule for vanadium, right? But we do have one for oxygen. And the rule for oxygen is that it's -2. So I'm going to write it algebraically. 2 vanadiums plus 5 oxygens has got to equal 0, right? If it were a polyatomic ion, if it were like -2, then it would have to add up to -2, okay? Let me move the bicarbonate further down. Okay. So now we're trying to find the vanadium. Vanadium is the one that we want to do. So let's put in our -2. So 2V plus 5 times -2 is equal to 0. 5 times -2 is -10. So 2V minus 10 is equal to 0. We add 10 to both sides. So we're just going through this algebraically. Add 10 to both sides. So 2V is equal to plus 10. We don't want to know what the oxidation state of 2 vanadiums are together. We want to know the oxidation state of each vanadium. So we divide both sides by 2. And 10 divided by 2 is plus 5. Okay, so each one of the vanadiums is plus 5. Each oxygen is -2. Those would be the oxidation states in that compound. Now let's do the last one here. This is called hydrogen carbonate or bicarbonate. When you have these ions that can have 1 hydrogen or 2 hydrogens, if it has 1, we call it bi. So this would be called bicarbonate, but technically it's called hydrogen carbonate. So with this one, it's a polyatomic ion. So that means it has to add up to the charge. The charge is right here, -1. So it has to add up to -1. So what I'm going to do is I'm going to break this down algebraically. 1 hydrogen, 1 carbon, 3 oxygens. It's got to add up to -1. Okay. Doesn't matter how many you have in there, but you do have to know some of them. So we do have a rule for hydrogen. The rule for hydrogen is +1. We do have a rule for oxygen is -2. That's got to add up to -1. So let's combine some terms. We have +1 and 3 times -2, that's -6. -6 +1 is -5. So really it's carbon -5 equals -1. All right, I've just combined these two terms here to get -5. Add 5 to both sides, right? If you have C -5, you add 5. So add 5 to both sides. And if you add -1 and +5, you get +4. So I think that was actually what carbon often works out to be. When carbon is combined with oxygen, it is very often comes out to +4. So there it is, +4. I'm sorry, there's only 1 hydrogen. Hydrogen is +1. And then each oxygen is -2, right? And there's 3 oxygens. So all of those numbers added together, you could draw a little picture, right? You could draw your carbon, you could draw your 3 oxygens, and then you could draw a hydrogen. And if you put in those numbers, +4, -2, -2, +1, -2, if you add all those together, you get -1. And that's exactly what we were looking for. Okay. So that's how you assign oxidation states or oxidation numbers. And again, the reason that we do this is that if an atom or an element changes its oxidation number from reactant to product, that tells us it's a redox reaction. So an example of that would be CH4. I'm going to show you an example.
Can you say that again? If an atom changes its what from reactant to product?
If it changes its oxidation number from reactant to product, that tells you it's a redox reaction. So here's an example of a redox reaction. Okay.
Professor, quick question before you begin that. For the past example, for the polyatomic ion example you did, wouldn't you multiply the 3 times the -2? No?
Yeah, exactly. So H plus C plus 3O equals -1. So +1 plus 4 plus 3 times -2. And that's going to add up to -1.
Okay, got it. Thank you.
So now let's take a look. I'm just going to look at carbon. So let's just worry about carbon here. If you think about it, these compounds, the CH4 and the H2O, they're not all that different, right? You got a carbon with 4 hydrogens, you got a carbon with 2 oxygens. This is combustion. This is an example of combustion. Combustion is redox. Okay, so let's go through it. We got the carbon here. Now that's a molecular compound, so it's got to add up to 0, right? Compounds, it has to add up to 0. We do have a rule for hydrogen, which is it's +1. So that means carbon plus 4 times +1 has got to equal 0 because it's a compound. So, you know, if you think about it, just sort of mathematically, if you have 4 times +1, that's 4, right? Plus 4. So in order for 2 numbers to add up to 0, one of them has to be negative, right? If you're adding 2 numbers and they have to add up to 0, one's got to be positive and the other one's got to be negative, or they both have to be 0, which I guess that could happen. But we got +4. So that means the carbon's got to be -4, right? -4 plus 4 is 0. But, you know, algebraically, what you would do is you would subtract 4 from both sides. And you get -4. So in this case, carbon is -4. That's very negative. And we can argue that one of the things that makes methane such a powerful reducing agent, such a powerful energetic molecule for us that we can use, you know, a Bunsen burner or a stove using natural gas. We can compress the natural gas into a liquid and drive buses around with it, right? So all that energy comes from the fact that carbon is at -4. And when it reacts with oxygen, it changes its oxidation state dramatically. So let's look at CO2. What happens to carbon over here? Well, again, we have carbon. We have 2 oxygens. And it's a compound, so it's got to add up to 0. We do have a rule for oxygen. Oxygen is -2. So carbon plus 2 times -2 is equal to 0. That's -4. Now be careful. The other one was C plus 4 equals 0. Now it's C minus 4 equals 0. So that carbon is not going to be -4 again. It's going to be +4. Okay? Because you add 4 to both sides and you get +4. So that carbon has changed its oxidation state from -4 to +4. Now, physically, what that means is this. You have carbon attached to 4 hydrogens. And it has an oxidation state of -4. Which in a sense is saying that it's electron rich. It has a lot of electrons, a lot of negative oxidation state. What happens is the oxygen molecules, okay, let me draw them. Let me draw them a little more, kind of like we do. Okay, Notice the stoichiometry, right? For every one of these, you need 2 of the oxygens, 2 O2s. So you have 2 of these. Those oxygen atoms, essentially, they get into this molecule and they start ripping out electrons. Each oxygen is going to rip 2 electrons away from that carbon. And the result of that is now you get carbon dioxide. And now the oxidation state of the carbon is +4. It's lost, effectively, it's lost 8 electrons. Its oxidation state has changed by 8, from -4 to +4. There's an enormous amount of energy change with redox reactions when that kind of thing happens. In fact, a lithium battery, in a sense, is much more modest. It's really lithium going to lithium plus. That's what happens in a lithium battery. It's really just changing by 1 electron. That's not a big change. Here we're talking about 8 electrons. So there's a lot of energy associated with that. Okay. Okay. So that's how you can tell. So anytime you're faced with an issue, you're looking at an equation and you're trying to figure out if it's a redox reaction. Well, one way would just be to memorize, oh, combustion, I recognize it as a combustion, or single replacement. But another way, more kind of formal and more inclusive, you can do it for any of them, is just start assigning oxidation numbers to all these elements and see if anything changes. If nothing changes, it's not a redox reaction. Hydrogen didn't change here, right? It's +1 there, it's +1 there. The other thing that did change was the oxygen. Since O2 is an element, it's -2. I'm sorry. Since it's an element, it's 0. Right? Elements are 0. O2 is 0. But here, it's in a compound, so it's -2. So you can see the oxygen changed too. The oxygen went from 0 to -2. That right there tells you it's a redox reaction. The carbon went from -4 to +4. That also tells you it's a redox reaction. So if you're just trying to tell if something's a redox reaction, you don't have to do every element. Once you find one element that changed, that right there tells you it's a redox reaction. Now, in general, if one thing changes its oxidation state, 2 will. One will lose electrons and the other one will gain electrons. Okay. So you generally don't have reactions where something gains, where did it get the electrons from? If it gained electrons, it had to get it from something. In order to get electrons, something else had to lose electrons. Okay. The reducing agent is the one that loses the electrons, and the oxidizing agent is the one that gains the electrons. In fact, the whole terminology of oxidation and reduction comes about from oxygen. Okay. If you look at the carbon, what happened to the carbon? It went from having no oxygens to having 2 oxygens. So it got oxidized. When something gains oxygen, it gets oxidized. When something loses oxygen, it gets reduced. Okay. You can't really see that in this particular equation, but when something loses oxygen, it gets reduced. Reduction of oxygen, right? You have less oxygen, so you got reduced. So let's take a look at the next question. And this one has to do with identifying redox reactions. Oops. Close that because it might mess up our meeting.
Are all redox reactions kind of like an explosion in a sense, because it has to do with oxygen, which is really a very combustible kind of gas?
Well, oxygen is important because it's 21% of the atmosphere. And so many reactions, like almost every element reacts with oxygen. There are a few that don't, right? Helium doesn't react with oxygen, right? Helium is a noble gas, neon, argon, krypton, and xenon. So the noble gases don't react with oxygen. For the most part, gold doesn't react with oxygen either. And that's why you can find gold in the form of little nuggets on the Earth's surface, is because it doesn't react with oxygen. All the other elements, some except, silver Silver is pretty inert as well. So silver will react with oxygen, but not as strongly as the other elements. But almost all elements react with oxygen. So that's why we can't really find lithium metal in nature. You can't just go to a mountain and dig out lithium metal. If there's any oxygen around, and there is a lot of oxygen on the Earth, the oxygen will oxidize it, and it'll be lithium plus in the form of a compound. Same with all the metals. Iron, you don't find iron in the Earth. You find it as iron oxide, and then you have to, put it through some chemical processes to convert it into iron, right? So yeah, the reason oxygen is so significant, and that's why, the terminology oxidation reduction comes from oxygen, is because it's so plentiful that that's what the early chemists were able to analyze. They were able to see that, oh yeah, if something reacts with oxygen, it got oxidized or reduced if it lost oxygen. But once the understanding of the atomic nature of matter, once we started realizing that matter was made up of these little particles called electrons, then we were able to expand, the chemists and physicists were able to expand the definition of oxidation and reduction to include other things that don't have oxygen in them at all. So for example, a lithium ion battery, they go to great effort to keep oxygen out of the lithium ion battery. It's encased in a plastic seal, and that keeps water vapor out and it keeps oxygen gas out. They don't want oxygen in there. They want the lithium to be reacting, and they want carbon to be reacting. So you got to keep the oxygen out. Otherwise, the oxygen would foul the battery and it would react with everything. So not all reactions with oxygen are explosive, but many of them are, right? So if you want to put a rocket into space, you need an explosion, right? That's what a rocket is. It's a controlled explosion. So with that, you're going to very likely use oxygen as the oxidizing agent. But gaseous oxygen, which we breathe in, isn't even really concentrated enough to make a rocket. You can't make a rocket out of gaseous oxygen. So you got to liquefy it. You have to cool it down to such a low temperature that the molecules are very close to each other, and you've got a liquid oxygen. Now you've got a very reactive substance. Liquid oxygen is more reactive than gaseous oxygen, and will react faster in any case. So many redox reactions don't include oxygen, but many do. But it is, you're right, it is a very powerful oxidizing agent, and it is believed that when photosynthesis was first developed on the Earth, probably 99% of all previous species went extinct very rapidly, and it changed the climate of the Earth. And I've even read that because of the loss of life, that changed the geology of the Earth, in fact, and the Earth actually froze and life almost went extinct. And so, this oxygen is a pretty amazing substance, actually. Fluorine is even more powerful as an oxidizing agent, but it's relatively, it's just not as plentiful as oxygen. There aren't any biological processes that form F2, like there are biological processes that form O2. So we don't really see very much fluorine out in nature here. So it doesn't, people did try to make rocket fuel out of fluorine, and it works. But if the rocket explodes, it'll kill a lot of people. So for that reason, they don't use fluorine. Oxygen's a lot easier and plentiful.
So why was it that you said that when you said acid-base reactions are not oxidizing reactions, but you do have oxygen in base reactions? So I wasn't sure what you meant by that.
So if you take a look at, let's take, for example, the simplest, really in a sense, the simplest acid-base reaction, which would be hydrochloric acid, for example, with sodium hydroxide. Okay, so hydrogen's +1, it's compound. It's compound, so the chlorine's got to be -1, right? So there's your oxidation states there. This is a ionic compound, right? So you got your sodium, which is +1, oxygen is -2, hydrogen is +1. So there's the oxidation states of the reactants. And then, the products are going to be a salt and water, right? So sodium chloride and H2O, right? There's your products. Well, if you go through and you analyze this, here's what you end up with. The issue is, can the oxygen, which is our most powerful oxidizing agent outside of fluorine, is there anything that it can oxidize in this reaction? Now, it can't oxidize the hydrogen because hydrogen's already oxidized. It's already +1. So there's nothing you can do to the hydrogen in terms of redox chemistry. The sodium, same thing. Sodium's already +1. If sodium were 0, then the oxygen could oxidize it and you get a redox reaction. But it's already at +1, so it's already oxidized. You could argue, well, what about the chlorine? Why can't the oxygen oxidize the chlorine? And the reason is oxygen is already at -2. So when we look at our combustion reactions, oxygen starts off as 0, and then it goes to -2. That's what oxygen is trying to do in terms of redox, is trying to get to -2. It turns out -3 is not stable for it. -4 is not stable. So it kind of stops at -2. Well, it's already at -2 here. It's already at -2 here. So there's nowhere really for it to go. So it becomes, in terms of redox chemistry, it becomes inert. It becomes unreactive. So that means that redox can't happen. So what else could happen? Well, there's a separate physical process, which is the idea that there's something stable about that molecule right there, that H2O. That H2O is very stable. So anything that has H plus and OH minus in the same solution, those two are going to be attracted through each other through acid-base chemistry. So you bring up an interesting point, which is there a hierarchy of chemical reactivity? Does a redox reaction become higher in hierarchy to an acid-base reaction? I would argue, yes, it does. If there were a way for something to get oxidized or reduced in this reaction, that would happen first. And then the acid-base chemistry would follow from that. But since all of these elements are already in their more stable oxidation states, that's not going to happen here. So that means anything else that could happen, well, there could be a precipitation or there could be an acid-base. The acid-base chemistry would come next. That's a good point. Interesting. Okay.
Thank you.
Now, yeah, there are acids that are really cool. Like there's this acid called nitric acid. And nitric acid is an acid. It's a strong acid. It's one of those 7 strong acids that I recommend you memorize. But it's also an oxidizing agent. So it actually does both. So that gives it some very interesting chemistry. Okay. But we try not to really get into that kind of stuff in this course. That's kind of more advanced to think of things as being both an oxidizing agent and an acid or a base. You know, that's pretty advanced material. Okay, so let's take a look at this identifying redox reactions. So in this question, we're just trying to tell whether something is getting oxidized or reduced, okay? So again, it may be a little bit difficult for you to see it, but they're just doing it to one element, right? So the first one is just carbon in red. So the question is, well, you know, this is not that different. I mean, it is different, but it's similar to the one we looked at before, right? What you would do is you would assign an oxidation number to the element here, and then assign an oxidation state to the element over there, right? And see if there's any change. And if there's a change, it's a redox reaction. But now what we want to do is we want to go a little bit further and say, hey, did it get oxidized or did it get reduced? Okay. And in a sense, that first one, you could answer it without even understanding what the electron is, because with the first one, it gained oxygen, the carbon gained oxygen, so it got oxidized, right? You can go back to the pre-modern definition of what oxidation is, which is it gains oxygen. So since that carbon gained oxygen, you can tell it got oxidized. Feel free to use that, right? Like if you see that, you can always use that, but we want to do it in terms of oxidation numbers. So let me go through this one, and I'm going to give you the sort of analysis of this. Okay, so the idea is if an atom becomes more positive in the reaction, it got oxidized. Okay, I'm trying to put that into kind of simple words. The wording that they used to use for this was kind of so confusing, because they would use the terminology, it's higher in oxidation state or lower in oxidation state. And that can be confusing what that means. If it becomes more positive, it gets oxidized. And the way that I remember this is that if something becomes more positive, it lost electrons. More positive means you lose electrons. And so losing electrons is oxidation. Let me write that down. Losing electrons is oxidation. And the way I remember that is Leo. Okay. And then if you lose electrons, you become more positive, right? This is going to lead you to becoming more positive because you're losing negative charge. And then the reverse of that is that reduction, I'm sorry. The reverse of that is that the gain of electrons is reduction. So reduction, you become more negative, okay? So if an atom becomes more positive in the reaction, it got oxidized. If an atom becomes more negative in the reaction, so let me get rid of that. You could misinterpret that, right? More negative in the reaction, it got reduced. So the idea here is Leo goes grr. It's the lion. Leo the lion goes grr, growls, right? So losing electrons is oxidation. You'll get more positive. Gaining electrons is reduction. You become more negative. There's a second one that I'm aware of. There's probably a third one too, and that's oil rig. And that is oxidation is loss of electrons, right? Reduction is gain of electrons, right? You just have to remember that if you gain electrons, you're going to become more negative because electrons are negative. If you lose electrons, you're going to become more positive because electrons are more positive. Okay. Now, we did a lot of going through the oxidation numbers. So for the first one, let me just save this. So for the first one, I'm not going to go through, oops, sorry, I'm not going to go through actually calculating them because you can do that. But I want to go through the logic of this. Okay, so the logic is this. If you go through the carbon here in the first one, you end up with -4. We just did methane actually as an example, right? Methane, carbon was -4. And then over here, the carbon is +4 because each oxygen is -2. So it went from +4 to -4. That means it became more negative. That means it gained electrons. Gain electrons is reduction, right? Gain electrons reduction, grr, or reduction is gain, right? So in this case, the carbon, I'm sorry, it went from -4 to +4. It lost electrons, so it got oxidized, okay? So I think I said it the reverse. So let me be careful about that. Here it's -4. Here it's +4. So it became more positive. That's losing electrons. So that's oxidized. Let's take a look at the second one. The second one, the O2, well, that's an element. So it's 0. So here it's 0. Here in water, it's -2. Right? In a compound, oxygen is -2. So it went from 0 to -2. That's a gain of electrons. A gain of electrons is reduction. Okay, so in this case, the oxygen got reduced. Now let's take a look at this one. This is copper sulfate, and then copper. So here, this is not obvious, but this is an ionic compound. This is sulfate. Sulfate is -2, right? SO4 -2 is the polyatomic ion. Copper would be +2. So copper is what we're interested in here, is +2. Here it's an element, so it's 0. Now this is a little tricky in terms of thinking about numbers. If something starts as +2 and it becomes 0, that is becoming more negative, right? 0 is more negative than +2. So really what happened was it went from having a charge of +2, gaining 2 electrons to become 0. So that's a gain of electrons. So the copper, in fact, got reduced. Reduces when you gain the electrons. Okay. And the last one, carbon, that's an element, so it's 0. Here it's in a compound, it comes out to +4, right? Because each oxygen is -2, and they have to add up to 0. So it went from 0 to +4. That's becoming more positive, which means you lost electrons. Okay, loss of electrons, Leo, loss of electrons is oxidation. So that means the carbon got oxidized. Okay, now in this particular problem, anytime something gets oxidized, the other one's got to get reduced. So if carbon got oxidized, that tells you the oxygen got reduced, but they're not asking you about that. But be aware of that, that if something happens to one, the opposite happens to the other, because they're competing for electrons, right? What we're claiming here is the oxygen is taking electrons from the carbon. So just as the copper here went from +2 to 0, so it gained electrons, the zinc went from 0 to +2, so it lost electrons. Just as the oxygen here is gaining electrons, so that's reduction, the hydrogen is losing electrons, that's oxidation. And likewise up here, the carbon is losing electrons, getting oxidized. It's actually let's see, it's the hydrogen. The hydrogen, which is +1 here, is becoming 0 here. So it's gaining electrons. The hydrogen is getting reduced. Okay. So one substance gets oxidized, loses electrons, becomes more positive. The other substance gains electrons, becomes more negative, and that's reduction. Oxidation, reduction, redox. Okay. Let's see. Just about out of time here. These are all pretty similar here. But I want to show you one where it's actually neither, right? Because all of those were redox reactions. I'm going to draw your attention here to the second one, where we have 2 NH3 plus H2SO4 to form NH4 2SO4. Well, let's go through the nitrogen. Don't worry about coefficients when you're doing oxidation. The coefficients are important in terms of calculating how many electrons were transferred, but it's not important in terms of identifying whether it's a redox reaction. So you can ignore the coefficients for these problems. So hydrogen is +1. There's 3 of them. So that's +3. So that means the nitrogen's got to be -3. Okay. Now let's look at the nitrogen over here. That's a complicated compound, right? But it's simpler if you break it down into polyatomic ions. The sulfate is SO4 -2. That's a polyatomic ion. So you can just kind of break that off. Each of these is a polyatomic ion, NH4 plus, right? So there's 2 NH4 pluses and an SO4 -2. So now really all you got to do is analyze NH4 plus, okay? Each one's going to be the same. So NH4 plus has 4 hydrogens, 1 nitrogen, and a positive charge. It's a polyatomic ion. So that means you've got 4 positive ones, each hydrogen's +1, so that's +4. So let me go through it real quick and then we'll finish this up. Okay, so really what you're going to do is you're going to break it up into polyatomic ions. You got SO4, -2, and then there's 2 of these. Right, that's what that 2 means there's 2 of them. We're just interested in the nitrogen. That's the only one we're interested in. So let's just figure out what nitrogen is, okay? Well, polyatomic ions, so nitrogen plus 4 hydrogens, it's got to equal the charge, +1. Each hydrogen is +1. Okay, so that's nitrogen plus 4 equals +1. Subtract 4 from both sides, and you get -3. So the nitrogen is actually -3 here. Okay, going back to the NH3 on the reactant side, nitrogen plus 3 hydrogens. It's a compound, so it's got to be 0. So that means the nitrogen is also equal to -3. So there was no change here. And this is the example I wanted to show you, where this is actually turns out to be an acid-base reaction, because you're taking ammonia, which is a base, and you're taking sulfuric acid, which is an acid, and it's forming a salt. And the salt is the ammonium sulfate. Okay. The nitrogen started as -3 in the form of ammonia, and it ended as -3 in the form of the ammonium ion. So that's not a redox reaction. In fact, that's actually an acid-base reaction. If you go through and you do the hydrogen, you'll find it's +1 on both sides. If you go through and you do the sulfur, you'll find that the sulfur is +6 on both sides, and the oxygens are -2 on both sides. So everything stays the same. Nothing changes in terms of oxidation numbers. And there you go. Okay. So this is going to hit the end of the week here. So what we'll look at next week, let me just bring this up here. We have 2 more types of problems to deal with in terms of redox, and then we get into the molarity calculation. So we'll start on Tuesday. So the next one is, again, the same idea. We're just identifying whether something's a redox reaction, yes or no. But now we're going to use a slightly varied terminology. We're going to talk about the reactants as being agents. So is something a reducing agent or an oxidizing agent? So we'll look at that. And then we'll look at writing. This is the second method of analyzing redox reactions. There's actually several. This is the second. We're just going to do 2. And that is what we call half reactions. So we'll talk about how to write half reactions. That's a different way to analyze redox reactions. So we'll look at that. And then we'll get into molarities. So we'll do those 2 on Tuesday. That might take the whole hour. Just depends how, how slow I talk, how fast I talk. And then if that takes the whole hour, then on Wednesday, we'll do our molarity calculations, and we'll wrap that up on Wednesday. Okay. So have a great day. Have a great weekend. Reach out to me if you have any questions, and I'll talk to you later.
Have a good weekend.
Yeah.